Okay, let's start with a little bit of review from our last video. Well, the electrical conductivity of the heart. So our electrical conductivity begins with our SA node. Our SA node resides in the right atrium near the entrance of the vena cava. So as blood returns from all the working tissues after it's deoxygenated and returns to the heart, it passes by the SA node, and the SA node has a property that's called automaticity, where it spontaneously depolarizes at a rhythm, giving it the nomenclature of a pacemaker cell. So it will spontaneously depolarize approximately every 300 milliseconds or so. So once we're in the SA node, let's start here. The pacemaker cells of the SA node generate an action potential, which travels down the internodal pathways around the right atrium, stops at the AV node. There's approximately a 0.1 second delay here in order to allow the atria to contract before the ventricles get the signal. So if there was nothing delaying it here, the atria and the ventricles would contract simultaneously, and the heart wouldn't work very well. There's also a layer here of connective tissue that separates the atria from the ventricles, and that gives us some insulation, a little bit of resistance, so that this electrical discharge through here, through the internodal pathways, doesn't distribute itself to the ventricles and cause a heartbeat that's beating out of time. After the AV node, we travel down the bundle of His. The electrical activity is there. To the bundle of His. Spelled His, but pronounced hiss like a cat hissing. Then we go to the left and right bundle branches, to the Purkinje fibers. The Purkinje fibers are just large diameter, rapidly conducting cells that are connected by low resistance gap junctions. It allows electrical activity to travel very quickly, and getting this electrical activity distributed throughout the ventricles. So that's our basic electrical activity, the mechanical electric activity of the heart. Now we need to talk a little bit about the action potentials within the heart. So an action potential within the heart, since it's a muscle, remember we had three types of muscle: skeletal muscle, cardiac muscle, and smooth muscle. Cardiac and skeletal muscle are the only two striated muscles, and they do have a similar type of action potential. But the main difference between the skeletal muscle action potential and the cardiac action potential is the introduction of a new ion called calcium. So let's draw our graph like this. We got membrane potential on our y-axis and time on our x-axis. So let's start down here at minus 100 millivolts, minus 50, 0, and slightly above. 0, okay, so this is a cardiac myocyte of the ventricle. So as an action potential occurs, our resting or our diastole is approximately 90 millivolts. So let's make this a little lower, minus 100, just to make it look better in diastole. And then we get this big peak like this, and then this plateau like that. So it's a little bit different than a skeletal muscle action potential in the fact that its time course is much longer. Remember, skeletal muscle was just like that with some hyperpolarization to prevent the cell from continuously depolarizing giving us an absolute refractory period at that point. So much like the action potential for the skeletal muscle, we have sodium entering the system right here, causing this big depolarization. At this point, you start to get some transient, oops, spelled it wrong. Transient potassium ions are leaving the cell. Right through here, the plateau is where calcium enters and potassium continues to leave. And as potassium continues to exit, we get repolarization. The interesting thing about this is, remember our Goldman-Katz equation, where we have the membrane potential equals RT, I think there's an F in there too, or yep, RTF, natural log, our permeabilities, of our permeabilities, potassium, and then in this case we're going to look at the permeability of calcium, because calcium is our new ion that we're introducing into the system. And remember, it's out, in. This would be reversed if they were negative ions or anions. Since they're all cations, we're looking at it from this way. So now that we know that these are the ions at play, we can start looking at the differences in permeability that are allowing this to happen in the cell. So let's draw another graph. 0.15, 0.3, and we're in seconds again. Should have labeled that. And over here, we have permeability. So we'll have 0.1, 1, 10. We're on a logarithmic scale. And our first ion that we talked about was sodium. Right here is sodium enters. It's going to enter at our same time. And we get a big peak of sodium, greater than a 10-fold increase. And it looks like that. That's our increase in sodium, our permeability of sodium. The next ion that we talked about was the potassium exiting the cell. So remember, if we looked at the Goldman-Katz equation from skeletal muscle, we remember that the permeability of potassium at rest was much greater than the permeability of sodium at rest. And this follows true as well. But we start out at 1, and at 0, we see this little hump right there, and then cross over, and we overshoot, and we get back to rest. So this is the permeability of potassium. Lastly, we have the permeability of calcium. So this is a little bit delayed. Our permeability is slightly below our sodium permeability. And right here, you got an overshoot. And then back. And this is our permeability of calcium over here. So these are the 3 ions that are at play in a ventricular action potential. But those are pretty interesting. So these ventricular myocytes or cells are eventually contract after this action potential has traveled down into the contractile proteins and allows them to contract at that point. Over here, you can see all the interplay of the ions.